Helicopters are incredible machines. They can hover, fly sideways, and land almost anywhere. But there's a trade-off most people don't realize. Helicopters are extremely energy hungry, especially compared to airplanes. And the reason why has very little to do with engines and everything to do with physics. In the next few minutes, I'll explain why helicopters consume so much energy, why electric helicopters are such a challenge, and what engineers are doing to fix it. Let's start with a key difference. Airplanes generate lift by moving forward. Once they're fast enough, the wings do most of the work efficiently. Helicopters don't have that luxury. To stay in the air, a helicopter must constantly push air downward, even when it's not moving forward at all. That means the rotor is always working. There's no coasting, no free lift. If the rotor stops producing lift, the helicopter drops. This makes hovering one of the most power-intensive things a flying vehicle can do. Engineers break down rotor power into several components, but the most important one here is induced power. Induced power is the energy required to push enough air downward to support the helicopter's weight. The heavier the aircraft, the slower the airflow, or the longer you hover, the more energy you consume. This is why helicopters use far more energy at low speeds than people expect. Flying slower doesn't always save energy. In fact, hovering or creeping forward can be worse than steady forward flight. Now let's talk about electric helicopters. Electric motors are actually very efficient. That's not the problem. The problem is energy storage. Batteries store far less energy per kilogram than aviation fuel. And remember, induced power depends heavily on weight. Add batteries, you increase weight, which increases power demand, which drains the batteries faster. It's a feedback loop engineers must carefully manage. This is where flight decisions become critical. How fast you climb, how long do you hover? When you transition to forward flight, two helicopters flying the same distance can use very different amounts of energy depending on their flight path. Gentle climbs, minimized hover time, and efficient cruise speeds can dramatically reduce total energy consumption. Energy efficiency isn't just about hardware. It's about how you fly. A common question is, why not just slow the rotor down? Or why not just fly faster? Because aerospace optimization is always a trade-off. Lower rotor speed might save energy, but it can increase vibration, reduce control authority, or affect safety margins. Faster flight might reduce hover losses, but increase aerodynamic drag. Engineers must balance energy, safety, noise, and performance at the same time. The future of efficient rotorcraft isn't one magic solution. It's a combination of smarter flight planning, variable rotor speeds, lightweight structures, hybrid and electric propulsion, and mission-specific optimization. Progress happens quietly through modeling, simulation, and careful design. If you enjoy explanations like this, where aerospace engineering is explained clearly without hype or oversimplification, consider subscribing. This channel breaks down how flight technology actually works and why engineering decisions matter in the real world. Thanks for watching, and I'll see you in the next one.